Hi guys, this is the EdExcel A-Level Maths Paper 2 from the October 2020 papers, and it covers the statistics section. Question number 1. We've got this histogram over here which shows the times taken to complete a crossword by a random sample of students, and the number of students who completed the crossword in more than 15 minutes is 78. We have to estimate the percentage of students who took less than 11 minutes to complete the crossword. Well, over here we've got the minutes along the horizontal axis, and along the vertical axis we've got the frequency density. And you'll also notice the frequency density axis has not been labelled. We've got some interesting information here. It took 78 students more than 15 minutes to complete a crossword. So what we can do instead is relate the number of squares to the number of students. Now, more than 15, the area would represent the total frequency. So therefore, you can see for more than 15, we have 36 plus 12 plus another 4, that's 52. So we have 52 squares, which represents 78 students. Let's just write that down. For more than 15 minutes, 52 squares represents 78 students. So therefore, we can find out what 1 square would represent. So therefore, 1 square, that would represent 78 divided by 52, which is 1.5. So 1 square would represent 1.5 students. And with this, we can find out the number of students who took less than 11 minutes to complete the crossword. Now, less than 11 minutes, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16 squares, which represents the number of students who took less than 11 minutes to complete the crossword. And with that, we can find out the number of squares and therefore the number of students. So we have 16 squares, and to find out the number of students, this represents 1.5 multiplied by 16, that would be 24. So 16 squares would represent 24 students. Okay? So, with this, we can find out the percentage of students who took less than 11 minutes. And we can do this by, first of all, finding out the total number of students, and from that we can find the percentage. So recognizing that 1 square represents 1.5 students, you can see here between 2 and 10, that's 8 squares. Multiplying that by 1.5, we end up with 12. So we have 12 students here. Here between 10 and 12, you can see that we've got over here 16 squares. Therefore, 16 times by 1.5, that's 24. You can see here between 12 and 15, we have 12 squares. 12 times by 1.5, that's 18. So here we have 18 students. Between 15 and 18, we've got 36 squares. And 36 times by 1.5, that's 54, so here we have 54. Between 18 and 22, we've got 12 squares. 12 times by 1.5, that's 18. So here we have 18. And finally, 4 times by 1.5, that's 6. So with this, we can find out the percentage of students who took less than 11 minutes. So we have 24, which is the number of students who took less than 11 minutes, over the total, which is the sum of all these. So if we work all of this out, working all of this out using our calculator, we have 24 divided by 12 plus 24 plus 18 plus 54 plus 18 plus 6, and then we multiply this by 100, we end up with 18.2%. So we have 18.2% to 3 significant figures. And of course, this makes sense even if we just consider the diagram. Question number 2. Jerry is studying visibility for Camborne using the large dataset June 1987. The table below contains 2 extracts from the large dataset. It shows the daily maximum relative humidity and the daily mean visibility. And we see here in this table, the units for daily mean visibility are deliberately omitted. They're not included here. For part A, given that the daily mean visibility is given to the nearest 100, we have to write down the range of distances in meters that corresponds to the recorded value 0 for the daily mean visibility. Now, in the large dataset, you should be familiar with all these units, but if you're not familiar, when we take a look at the large dataset, in the introduction section of this large dataset, under the tab labelled Information, we see that what's given to us is different pieces of information, and for visibility, we see over here that the values are denoted in decameters, dm for short. So we can use that information here and the information given here to write down the range of distances in meters. You'll notice here, meters is what we are required to give our answer in, even though what's shown here is in decameters. Okay, so let's just add this as an annotation. Daily mean visibility is usually measured in decimeters, and just as a conversion, because we want to give our range of distances in meters, to convert from decimeters to meters, we multiply by 10. And of course, from meters to decimeters, we would have to divide by 10. Okay, so with this, knowing that the values here are given to the nearest 100, what this tells us for the date of 10th of June 1987, where we have a daily mean visibility of 5,000 300, the range of values here would be 5250, which is less than or equal to V. Remember, the units of V are in decimeters, which is less than 5350. And if we consider the range of values for this particular date, 28th of June 1987, of course, V must be greater or equal to 0. That makes sense. The distance can't be negative. And if it's given to the nearest 100, and we have 0 over here, V must be less than 50. Okay? Now, these range of values I've written down over here are in decimeters. And we want to write these values down in meters, so we simply multiply by 10. So we see that the range of values, we have 0, which is less than or equal to V, which is less than 500. Of course, the units of V are in meters. So all I've done is multiplied the 50 by 10 to get that 500. Now for part B of the question, Jerry drew the following scatter diagram, shown here in figure 2, and calculated some statistics using the June 1987 data for Cambon from the large dataset. So we've got the daily maximum relative humidity along the horizontal axis, and along the vertical axis we've got the daily mean visibility. And we've also got this table over here. The table over here shows the lower quartile, Q1, the interquartile range for both the daily mean visibility and the daily maximum relative humidity as a percentage. Jerry defines an outlier as a value that is more than 1.5 times the interquartile range above Q3, or more than 1.5 times the interquartile range below Q1. And for part B, we have to show that the point circled on the scatter diagram is an outlier for visibility. Now, what this point circled here corresponds to in terms of a daily mean visibility, you can see over here, that's 5,300. So, what we can now do is, with this table here, find out the upper quartile Q3. So, here I've just copied out the table as given to us in the question, and with this we can find out what the upper quartile Q3 is. We know already that the interquartile range, that's equal to Q3 minus Q1, from which we can rearrange to say that the upper quartile Q3, that's equal to the lower quartile Q1 plus the interquartile range. So 1100 plus 1600, that will be 2700. 92 plus 8, that will be 100. So we can now use his definition to find out a range of values for which we do not have any outliers. So he said that we have an outlier when we have a value that is more than 1.5 times the interquartile range above Q3, or more than 1.5 times the interquartile range below Q1. So with this, let's find out a range of values which are acceptable, for which we have no outliers. So we have for our lower limit essentially 1100 minus 1.5 times by the 1600, which is minus 1300. So here we have minus 1300 for essentially our lower limit, and for our upper limit we have 2700 plus 1.5 times by 1600. We end up with 5100. So what we see over here is that value shown in the scatter diagram here, which corresponds to 5300, that's greater than what we've just found over here for the 5100. So what we see over here, since the 5300 is greater than the 5100, we can conclude we have an outlier. For part C of the question, we have to interpret the correlation between the daily mean visibility and the daily maximum relative humidity. We see over here that as the daily maximum relative humidity increases, the daily mean visibility decreases. So here we have a negative correlation. So what we'd put as our answer is, as the daily maximum relative humidity increases, the daily mean visibility decreases, and we see that through this negative correlation. Now for part D of the question, Jerry drew the following scatter diagram, figure 3 shown here, using the June 1987 data for Cambron from the large dataset, but forgot to label the x-axis. And using our knowledge of the large dataset, we have to suggest which variable the x-axis on this scatter diagram represents. Well, the way to think about this is, as one variable increases, the other also increases. And we can actually use a bit of common sense here. Of course, the more we can see, in other words, the greater the daily mean visibility is. Essentially, we want something that corresponds to this increase in visibility. And if we take our large data set, we've got various different statistics which are measured. So let's just read through them. We've got the daily mean temperature, the rainfall, the total sunshine, the relative humidity, and we've got other statistics shown here. And we've got the visibility and we've got the pressure. And if we actually take a look over here with our different columns, and of course you are supposed to be very familiar with all this, we can't choose these sort of data for our answer because these are qualitative. And what we could do instead, we could use the daily total sunshine in hours, and that makes sense for us to use that because as the number of sunshine hours increases, of course the visibility with that will also increase. So we have the daily total sunshine over a 24-hour period in terms of hours. And that makes sense, of course, as the number of hours of sunshine is increased, the daily mean visibility also increases. Question number 3. In a game, a player can score 0, 1, 2, 3 or 4 points each time the game is played. The random variable S, representing the player's score, has the following probability distribution where A, B and C are constants. the probability of scoring less than 2 points is twice the probability of scoring at least 2 points. And each game played is independent of previous games played. John plays the game twice and adds the two scores together to get a total. We have to calculate the probability that the total is 6 points. Well, to begin with, whenever I see a question like this, I think to myself, probability adds up to 1. So, if probability adds up to 1, we see here the probability of scoring a 0, which is A, plus the probability of scoring a 1, which is B, plus the probability of scoring a 2, which is C, plus the probability of scoring a 3, which is 0.1, plus the probability of scoring a 4, which is 0.5. All this is equal to 1. So we can simplify all this to say that A plus B plus C is equal to 0.75. Okay? We also know from the question that the probability of scoring less than 2 points is twice the probability of scoring at least 2 points. So what does this mean? It means over here the probability of scoring less than 2 points, so let's just write that down, the probability of scoring less than 2 points, well that's the probability of scoring a 0 and scoring a 1. So that's the same as scoring a 0 and then a 1. That's equal to twice the probability of scoring at least 2 points. Well, if we consider scoring at least 2 points, that's the probability of scoring a 2, scoring a 3, and scoring a 4. Okay? So if I multiply this by 2, we get this result here. So here, the probability of scoring less than 2 points, that corresponds to this over here. This is twice, so that's why we multiply by 2. The probability of scoring at least 2 points. So that corresponds to this over here. So if we use this information, the probability of scoring a 0 or a 1, that will be A plus B. And this is equal to 2 lots of the probability of scoring a 2, which is C, the probability of scoring a 3, which is 0.1, plus the probability of scoring a 4, which is 0.15. So, if we tidy all this up, we have A plus B, which is equal to 2C. Now here we have 0.1 plus 0.15, that's 0.25. Multiplying that by 2, we end up with 0.5. So with this, we can solve these equations simultaneously to find out the values of A, B, and C. Now, when we come to calculate the probability that we have a total of 6 points, you have to think about if calculating A and B is necessary. It won't be necessary, because the only way I can get a 6 is if I have the 2 and the 4, or the 3 and then the 3, or getting a 4 and a 2. So I don't need these probabilities of scoring a 0 and a 1 to work out the probability that we have a total of 6 points. We'll come back to that point later. However, if we solve these equations simultaneously, if I call this equation 1 and this equation 2, solving them simultaneously, we can substitute in equation 2 into equation 1. So if I substitute in equation 2 into equation 1, you'd see over here A plus B, that's equal to 2c plus 0.5. So we can replace the a plus b with the 2c plus the 0.5, and then we've got this extra c, so this bit is what a plus b is, and this is equal to 0.75. So we see here that 3c, that's equal to 0.25, and therefore c, that's equal to 1 over 12. Okay? And if you want, from this you can find out what a and b are, if you were to solve those simultaneously. And if I do that, we'll do this in a different colour for now. If I substitute this value of c into equation 1, we have, using equation 1 say, we've got a plus b plus c, which is 1 over 12. This is equal to 0.75, which if we rearrange, we see that a plus b, that's equal to 2/3. And if we use equation 2, for example, so using equation 2, we have a plus b, that's equal to, well, a plus b, that's equal to 2c, so here we've got 2 times by 1 over 12 plus the 0.5, so here we've got a sixth, sorry, here we've got, yeah, a sixth plus 0.5, that will be 2/3. Okay, so we've got a plus b, which is equal to 2/3, and a lot of you at this point will probably substitute into your calculator. So if we go to the simultaneous section on our calculator, we can solve those simultaneously. So with that, we see here our calculator tells us we've got an infinite number of solutions. And that doesn't make a difference in this question. It doesn't matter what a and b are, because we're not interested in it to find out the probability of scoring a total of 6 points. But we'll write it down for completeness. So we've got an infinite solutions for a and b, and we want to, in this question, find the probability of scoring 6 points in total. So the probability of scoring 6 points in total, here we've got the probability of scoring, say, a 2 in the first game and a 4 in the second game. Another way we can get a 6 is if we score a 4 in the first game and a 2 in the second game. So we can have a 4 and then a 2. Or we can get a 3 in the first game and then a 3 in the second game. So scoring a 2 in the first game, that probability corresponds to C, which we said was 1/12. And we have to get as well a 4. So that corresponds to the 0.15. Or we can get a 4 and a 2. So here we have the 0.15 multiplied by the 1/12. And the probability of getting a 3, that was 0.1. So here we have 0.1 multiplied by 0.1. And if we work all of this out, we have 0.15 multiplied by 1 over 12. We multiply this by 2, and then we add on, as we see here, 0.1 times 0.1. So we add on 0.1 squared. It turns out we get 0.035. So we end up with 0.035. Question number 4. A lake contains 3 different types of carp. There are an estimated 450 mirror carp, 300 leather carp and 850 common carp. Tim wishes to investigate the health of the fish in the lake. He decides to take a sample of 160 fish. We have to give a reason why stratified random sampling cannot be used. Well, over here we have to recognize a couple of things. The key in this question is to recognize that it's not possible to have a sampling frame. That's the most important reason. And just as a reminder of the definition of a sample frame, that's a collection of all sampling units. Also, the disadvantages of a stratified random sample: the population must be clearly classified into distinct data. Another disadvantage, it's not suitable when the sample size is large. But in the context of this question, we don't have a collection of all sampling units for this particular context. Now for part B, we have to explain how a sample of 160 could be taken to ensure that the estimated populations of each type of carp are fairly represented. So of course over here we can use quarter sampling, and if we think about the advantages of quarter sampling, no sampling frame is required. It allows for a small sample to be representative of a population, and it allows for easy comparison between different groups within a population. So our next step is to find out how many of each type of carp we need, and before we do that, let's talk about the stages of quarter sampling. So the population is divided into groups according to a given characteristic. In this case, the characteristic is the type of carp. Then the size of each group determines the proportion of the sample that should have that characteristic. So if we go back to our example, we see that we have 450 mirror, 300 leather, 850 common. So adding that up, we have over here 450 mirror, 300 leather and 850 common, and if we add those up we get 1600 carp in total. Okay, so with this we can find out the size of each group. So essentially we would have to use some sort of a scale factor, if you want to think of it like that. We've got k, which is equal to capital N over little n. So capital N, that's 1600, little n, that's our sample size, that's 160 fish. So we've got 1600 divided by 160, which turns out to be 10. And therefore, if we think about our mirror fish, for example, for the mirror, we've got 450 over this 10, which is 45. For leather, we have the 300 over the 10, which is 30. And for the common, we have 850 over 10, which is 85. Okay, and then finally, we then ignore any fish caught of a type when quarter is full. For part C of the question, as part of the health check, Tim weighed the fish. His results are given in the table below, and we have to calculate an estimate for the standard deviation of the weight of the carp. And we may use the sum of the FMs is equal to 692 and the sum of the FM squareds, that's equal to 3053. Well, what we can do is, if we take a look in the formula book, we can use this formula for the standard deviation. So what that means in our case, the standard deviation is given by this formula here. We know what each of these are. So we have over here 3053 divided by n. N over here is equal to 160. We have 160 fish in total in our sample. And then the mean, that will simply equal 692 divided by 160, and then we square it. And then we square root this entire result. So, if we work all of this out, let's use our calculator. We have the square root of 3053 divided by 160 minus 692 over 160 squared. It turns out we get 0.613 to 3 significant figures. Okay. Now for part D of the question, Tim realised that he had transposed the figures for 2 of the weights of the fish. He had recorded in the table 2.3 instead of 3.2. So instead of writing the 2.3, he should have put 3.2 instead. And instead of the 6.4, which he should have put down, he put 4.6 instead. Without calculating a new estimate for the standard deviation, we have to state what effect using the correct figure of 3.2 instead of the 2.3 has on the standard deviation, and then what effect would using the correct 6.4 instead of the 4.6 have on our estimated value of the standard deviation. Give a reason for each of your answers. Well, we'll consider this first case over here. And if you consider this first case, you'd see for this first interval here, instead of using 2.3, we were supposed to use 3.2. And the 3.2 still goes into this interval here. So when we come to work out the standard deviation, it will have no effect because the 3.2 still goes in this interval. So let's just write that down. So the 3.2 is still in the interval 2 to 3.5, and therefore there's no effect on the standard deviation. But if we go back, we see over here, if we use the 6.4, we see that that goes in a different interval because it can no longer belong in this interval 4.5 to 5. So what do we do in this case? Well, we see here 6.4 is outside any of these intervals over here. And 6.4, that's clearly larger than the 6 over here, the biggest possible value which was previously said. So what happens is, in terms of the weights are more spread out. So if the weights are more spread out, that will mean that the mean will increase by a small amount because this time we've got a bigger value to consider instead. And therefore, because the weights are more spread out, the standard deviation will also increase. So let's just write that down. So the 6.4 is outside any of the listed intervals given to us in that table, and this larger value of 6.4 will increase the mean by a small amount. Hopefully you can see why that's the case. Of course, we've got a bigger number to consider this time. And we also see that the data is more spread out, and that's as a result of it being outside any of the intervals. It's going to be outside the interval 5 to 6, and therefore the standard deviation will increase as a result of this. Question number 5. Afrika works in a call centre. She assumes that calls are independent and knows from past experience that on each sales calls that she makes, there is a probability of 1/6 that it is successful. Afrika makes 9 sale calls, and we have to calculate the probability that at least 3 of these sale calls will be successful. Well, this is a typical case of a binomial distribution. We've got the probability of success, and each sale call is independent of the other. So what we can do for this question is, first of all, let's the random variable c, so we will let c be the number of successful calls. Okay, now we have over here 9 sales calls, so we can see here c is binomially distributed with parameters 9 and 1/6. So we want to find out the probability that she has at least 3 of these calls which are successful. So we're looking at over here the probability that c is greater or equal to 3. And that's equal to 1 minus the probability that c is less than or equal to 2. So if we work this out using our calculator, we go to menu, we have a distribution over here, we have a binomial cumulative distribution. Click number 2, x here is equal to 2, n that's equal to 9, the probability that's equal to 1/6. It turns out we get, for the probability that c is less than or equal to 2, we get 0.8217, etc. So therefore 1 minus this, this is equal to 0.178 to 3 decimal places. Let's store this into a just in case we need it later on. For part B of the question, the probability of Afrika making a successful sales call is the same each day, and Afrika makes 9 sales calls on each of 5 different days. We have to calculate the probability that at least 3 of the sales calls will be successful on exactly one of these days. So the way we can approach this question is to think about what's going on. Well, we're finding out the probability of success for one of these 5 days. And for each of these 5 days, each day essentially we're making 9 calls. And the probability that at least 3 of these calls will be successful, that's equal to this 0.178 which we calculated over here, and that's for each day. So the probability of success essentially is equal to the 0.178, etc. So the way we can approach this question, again, we can use a binomial distribution because each of the 5 days are independent of each other. So if we let x equal the number of occasions when at least 3 calls are successful, we have x which is binomially distributed with the parameters 5, we're looking at 5 days, and we have this probability of success being 0.178, etc. And we're looking at over here the probability that x is equal to 1. And we can use our calculator for this. So here we have a binomial PD. X here is equal to 1, n is equal to 5, p is equal to this value which we've just worked out. It turns out we get 0.406 to 3 decimal places. Okay. Now for part C of the question, to check Rowan works in the same call center as Afrika and believes he is a more successful salesperson. To check Rowan's belief, Afrika monitors the next 35 sales calls Rowan makes and finds that 11 of the sales calls are successful. Stating your hypotheses clearly, test at the 5% level of significance whether or not there is evidence to support Rowan's belief. So for this hypothesis test, we first of all state our null hypothesis. Our null hypothesis, that's H0, that's when the probability is equal to 1/6. Our alternative hypothesis, H1, that's when the probability is greater than 1/6. So the way we can approach this is, if we think about it, we can find out the probability that there's more than 11 successful calls. And if that probability is greater than 5%, then we accept H0. So we first of all list our random variable. Each call is independent of the other, and we assume over here our null hypothesis for the probability of success. So if we let R equal the number of successful calls, we have R, which is binomially distributed, parameters 35 and 1/6. So we are looking over here for the probability that R is greater or equal to 11. So that's the same as 1 minus the probability that R is less than or equal to 10. So if we work all of this out, we have 1 minus, so let's just go back to the distribution section. We have a binomial CD variable. Here x is equal to 10, n is equal to 35, and p is equal to 1/6. So we end up with 1 minus 0.976, etc. So working this out, 1 minus this, that's equal to 0.023. Okay, and that's to 3 significant figures. And if we compare that with the 5%, we see over here that this 2.3%, which essentially is what this value is, so if I multiply by 100 to convert it into a percentage, we have 2.3%. This is less than the 5% that we are testing at. So therefore there's significant evidence at the 5% level of significance to support that Rowan has more successful calls than Afrika. Of course we rejected H0 here.